Okay, in this video I'm going to walk you through a series of problems that you'll find in the appendix to this, this lesson. These problems are related to problems that we'll do in the computer workshop. And one of the programs will be focused a lot on problems like this. We'll have another one that's focused more on epithelial transport. Again, I strongly encourage you to come. I strongly encourage you to be able to do these problems. The physiology on your exam, not going to be a real high percentage, but it is high impact, and I would encourage you not to game the system too much by just ignoring this content because it's hard, because it's going to come back to bite you. This will come back to bite you if you don't understand it. It's going to be used constantly in virtually every single organ system. The epithelial transport is relevant to virtually every single organ system. That should be apparent, I hope. We're going to do some fluid and electrolyte stuff in the next case. I strongly encourage you not to ignore that, to be able to do the problems, because it's going to come back to bite you when we do renal and we start to talk the pathophysiology of these fluid imbalances. And if you don't understand the fluid and electrolyte physiology, you're going to be getting a bad start. You're going to be playing catch up at that point. All right. Enough said. Let's do problem number one. So I like these kinds of problems. They're simple. They're not particularly realistic, but they're very simple, and they're a good way to demonstrate some of the effects of osmolarity on cell volume and permeate and impermeate molecules. So what I have here is I have a cell. It contains two kinds of molecules, X and Y. X can get across the membrane. It's membrane permeant. Y cannot. So I have this cell, and what I'm going to do is I'm going to drop it into a beaker of solution, let's say 1 liter of solution. Now the volume of this cell is like in the picoliter range, 10 to the minus 12th. The volume of the solution in the beaker, 1 liter. Okay, so we have a huge volume on the outside, okay, and a very, very small volume inside the cell. I'm going to drop the cell into this huge volume. So in this case, I have a beaker of solution that has 100 millimolar X, 100 milliosmoles per liter, and 100 millimolar Y, 100 milliosmoles per liter. So first, let's look at X and Y. On the outside of the cell, I have 100 and 100. That is a total of 200 milliosmoles per liter. That's the osmolarity of the solution outside the cell. The osmolarity of the solution inside the cell, 200 and 100, that's 300 milliosmoles per liter. This is less than this, so we say that the solution outside the cell is hypoosmotic relative to what's inside the cell. Okay? Hypoosmotic relative to the inside of the cell. Okay? This is our reference. This is our solution that we're characterizing. All right? So now we know the osmolarity, relative, hypoosmotic. Now we say, what's going to happen to this cell when I drop it into the beaker? Is it going to swell? Is it going to shrink? Is it going to stay the same volume? Okay, so we drop our cell in, and now we have an osmotic gradient. You can see 300 here, 200 here. All right, the first thing that's going to happen, because X can get across the membrane, it's going to move down its concentration gradient, in this case from high concentration in the cell to low concentration outside the cell, from 200 to 100. X moves out, okay? And as X moves out, the concentration of X drops. And it's going to drop all the way down to 100. Now, the most common question I get asked about these problems is, why does it go all the way to 100? The reason is because the volume inside the cell is really, really small. So in order to move this concentration from 200 to 100, I only have to move a little bit of X. Okay? So I move that little bit of X from inside to outside. Well, that little bit of X makes a big difference in here when you're talking about picoliters of water. It makes almost no difference here when you're moving it into a liter of water. So this concentration effectively doesn't change. It's constant. And the only changes that you get in this problem are inside the cell. So you get a drop all the way down until X is the same inside and outside the cell. X moves across the membrane from inside to outside until it's the same concentration. Because the volume is really high here and really low here, it's going to move until the concentration is 100. The same on both sides. So now I've moved X. Now let's total up our osmolarity. I have 100, 100, I have 200 milliosmoles per liter here. I have 100, 100, I have 200 milliosmoles here. After moving X, I have the same milliosmoles per liter on both sides of the membrane. I have not moved any water, so we say that the solution is isotonic. So it was hypoosmotic, but because it doesn't do anything to cell volume, we say that it is isotonic. That is, the cell will not swell, it will not shrink in the solution, okay? This is a biological property. Will the cell swell or shrink? This is a physical property. I knew this before I ever even dropped the cell in, because I knew what these concentrations were. I could just add them up, okay? All right. Problem 2. 200 of X, 100 of Y, 300 total inside the cell. 100X, 200Y, 300 total outside the cell. The outside has the same milliosmoles per liter as the inside of the cell, so we say that our solution is isoosmotic relative to the inside of the cell, okay? This is our reference solution. I'm defining that for you, okay? All right. What will happen to the cell if I drop the cell into a beaker of this solution? One cell, picoliters here, big beaker, 1 liter here, okay? X moves across the cell from high concentration, 200, to low concentration, 100, because it's permeant, Y is not. So once again, X drops to 100, and I have the same concentration of X now on both sides of the membrane. Now, what's our situation? I have 100 here, 100 here. I have a total of 200 milliosmoles per liter inside. I have 100 here, 200 here. I have 300 milliosmoles per liter outside. So I have high osmolarity here, low osmolarity here. Now, Y can't move across the cell. Okay, I'm done moving X. Y can't move because it's membrane impermeate. So instead of moving Y, I'm going to move water. And what's going to happen is water is going to go from high concentration, that is low osmolarity, to low concentration, that is high osmolarity, and the cell shrinks. And water moves until Y goes from 100 to 200. Because I'm decreasing the volume, my concentration of Y goes up as I move water, and I move water until I have 200 here and 200 here. And now I have 100 and 200, 300 milliosmoles per liter here. I have 100 and 200, 300 milliosmoles per liter here. I have the same osmolarity on both sides of the membrane now, and I moved water to make that happen, which means my cell shrank. And so my solution is hypertonic. That is, it causes cells to shrink. If I drop the cell into the solution, the cell shrinks. Okay? Isoosmotic, add them up. Before you do anything, figure out what your solution is, in this case, relative to the inside of the cell. Isoosmotic relative to the inside of the cell. Hypertonic causes the cell to shrink. Okay? All right, let's do another problem. Now here I have, again, 200, 100. And now I have 300 of X on the outside and no Y. Okay, 0 Y. So now I can add them up, 300 milliosmoles per liter, 300 milliosmoles per liter. That is isoosmotic, right? Now, what's going to happen to the cell if I drop the cell into this solution? Well, the first thing that's going to happen is X is going to move, and it's going to move from high concentration, 300, to low concentration, 200. And it's going to move from high concentration to low concentration until I have the same concentration on both sides of the membrane. All right? I can't move Y, but I have 100 of Y here. I have 400 milliosmoles per liter, and I have 300 on the outside after moving my X. So now I'm going to move water, right? And I'm going to move water from lower osmolarity to higher osmolarity. Water moves into the cell. And we're trying to get Y to move we're going to move water in until the concentration of Y is equal on both sides of the membrane. We've already equilibrated X, now Y has to move. So we're going to try to drop Y to 0. Well, can we drop Y to 0? No. You can never move enough water into the cell to dilute this to the point where you've got 300 milliosmoles per liter. Because you can't get Y down to 0. There's always some Y in the cell. It can't get across the membrane. You're moving water, you're dropping the concentration, and you just move water, and move water, and move water, and you try to get this concentration to 0, and you can't. Because in order to get to 0, you'd have to have no Y. And of course, that won't happen. So what happens is you move water until the cell bursts, and you rupture the cell. Okay? And so this solution is very hypotonic. It causes the cell to not only swell, it causes it to swell till it bursts. Okay? So we started out isoosmotic, but it actually damages the cell when you put it in the body. Okay? Or when you put the cell into the solution. Okay? So, all right. So that's problem number 3. I have one more problem to do for you here. We have a typical liter of plasma, 5 liters of plasma, okay? 5 liters, 5 liters of red blood, 2 liters of that is red blood cells, 3 liters of that is plasma, and that is typical, okay? So this would be, blood in your body. You actually have 5 liters of blood in your body, so this would be comparable to doing something to the blood in your body. Let's say that you put 1 liter of water into the blood. This would be an accident because you would never do it, okay? Don't try this at home, kids. But let's say you accidentally did that. What would happen? What would the final red blood cell volume be? Okay, if I put 1 liter of water into your bloodstream, so I have 5 liters of total blood, 2 liters of that is red blood cell volume. I add a liter of water, what's the new red blood cell volume? Okay, well, in order to do this, the key is to find out what the new total osmolarity is going to be, and that's going to tell you what the new osmolarity inside and outside the cells is. So what I mean by that is, first, calculate the total number of milliosmoles, both inside the cells and outside, so the total number in the blood. So if I have 2 liters of red blood cells at 300 milliosmoles per liter, which is normal, then I have 600 milliosmoles of particles in the red blood cell. And we're going to say that all solutes are membrane impermeant. None of them can get across the membrane. So we have 600 milliosmoles in the red blood cell, 3 liters of plasma at the same osmolarity, because we know it has to be the same inside and outside, gives me 900 milliosmoles in the plasma. If I add those two together, that tells me I have 15 milliosmoles in 5 liters of blood in your body. Okay? And again, we're going to say all these particles are membrane impermeant. They can't get across your membrane. Okay? Now, if we calculate what the total blood osmolarity, remember it starts at 300, what that's going to be once we add water, we take that 1,500 milliosmoles and we divide by the new volume of blood, which would be our original 5 liters plus the 1 liter of water that we added. So this is 1,500 divided by 6. That gives you 250 milliosmoles per liter. So your new red blood cell volume is going to be such that you have 600 milliosmoles in the red blood cells, and you're going to have a concentration of 250 milliosmoles per liter, or an osmolarity of 250 milliosmoles per liter. Because if this is the osmolarity of the blood, then that has to be the osmolarity of the plasma and the red blood cells both, okay, at steady state. So we take our 600, and we say 600, 250 milliosmoles per liter is equal to our 600 milliosmoles divided by our new red blood cell volume, okay? If we take our 600, we divide by 250, our units cancel out and we get 2.4 liters of red blood cell volume. In other words, we had 600 milliosmoles in both situations because the particles couldn't cross the membrane. But we have a new osmolarity, and that osmolarity inside the cells is the same as the osmolarity outside the cells, which is the same as the total osmolarity in the blood as a whole. So if we calculate the new total osmolarity, that tells us what the osmolarity is of the red blood cells. And so we take our 600 milliosmoles and we just say, okay, what's the new volume got to be in order for the osmolarity to be 250, and it has to be 2.4. So my 1 liter of water caused those red blood cells to swell from 2 liters to 2.4 liters. That's a lot of swelling, okay? So don't do that, right? Okay, so that is the end of our problems. We'll pick up more problems related to that in the computer workshop, and again, I expect you to be able to work those. I will see you there, and I will see you in the rooms for the flu case. Thanks.